deep learning. Agree to recording here, 1 second. This is talking about deep reinforcement learning. I work in reinforcement learning and in deep learning, and sort of there's been some amazing successes of this domain in recent years, which probably many people have heard about, but we've probably all heard about the breakthroughs in Atari game playing, in AlphaGo, winning world, beating the world leaders in Go, and domains like OpenAI, at this point having a world-class set of players for the game Dota. And these are really sort of amazing, impressive things, right? These are tasks that I think we as a community, at least I didn't expect them to be solved for at least another 10 years or something like this. And deep reinforcement learning really has brought a new suite of capabilities to domains like this, and a new set of tools that we can bring to bear on really, really hard, long-term planning control problems, things like this. But there's also sort of a strange disconnect here. Because if you think about what seems to be much simpler domains, and that would be something like, I actually, to be clear, I don't mean an autonomous car as a whole, but something like just the control system of an autonomous car, just keeping lanes and things like this on a road. There's relatively little application of deep reinforcement learning and things like this, right? So in some sense, simple control systems, even ones that frankly could benefit from a bit of learning and optimization in the loop, don't yet integrate kind of all these things we've learned from deep reinforcement learning over the past 10 years. Now, of course, you could argue that this control is a small part of actual autonomous vehicles, but I would still argue that the control problems in autonomous vehicles are still things that are yet to be solved, and they are things that we still want to. We would like to be able to incorporate learning control into these things, but we aren't, or at least we aren't using techniques like this yet very prevalently in sort of real fielded systems. And in some sense, the reason for this is that the fields of deep reinforcement learning and the fields of control, or in this case, kind of this using robust control as a moniker for all of this, they've taken on very different sort of tacks as the fields have gone, right? So deep reinforcement learning really is about performance. It's about getting the sort of the best bang for the buck that you can, and it's about finding kind of the best policies we can, which work well in expectation, but which have to do some sort of things you wouldn't want to do in a real system, right? Because oftentimes there's very little knowledge of the system a priori, and so we have to integrate things like exploration, potentially exploring unsafe actions, and having very expressive policies that, especially while learning, can make very bad choices. So that the Dota players that you saw took many years of effective self-play against itself before it could actually learn how to play well against humans. And this is something we probably don't want. We don't want years of driving before we learn how to stay in a lane, things like this. On the other hand, robust control, the field of robust control as it's evolved, is really all about stability. It's all about guarantees. It's all about, on the other hand, though, it's all about very sort of simple, typically linear policies, right? So the trade-off you get for things sort of having guarantees is that you typically need to use very simple, not very expressive policies. And this limits the scope of what we can actually accomplish in these settings. And so what this talk is about at least getting towards bridging these two worlds, or at least getting towards that end of trying to bring these two a little bit more together than they currently are. So the way we're going to do this is we're going to sort of take on a view of the field of robust control, or the sort of the specifications that robust control typically thinks about. And we're going to think about whether we can enforce similar things in the context of more arbitrary deep learning systems. So that's sort of the rough outline of this talk, and I'll talk about how we do this in a moment. One thing I do want to mention, though, is please do enter questions during the talk anytime. I'd much rather sort of skip through my last few slides, or rush through my last few slides and have an interactive talk than just talk for 20 minutes or 25 minutes to finish all my slides. But so please do either use the raise hand or just enter in the chat if you have any questions as we go. So the starting point for how we do this, how we're going to start bridging these two kind of different worlds here, is we're going to talk about robust control specifications. And so we're actually going to start on that right-hand side of that previous slide, where we're going to start with what does robust control currently kind of consider as its starting point. And there are many different frameworks for robust control. I will emphasize that there's no one framework for robust control, but a very sort of common notion of robust control is that we model some system of interest as being a what's called a linear dynamical inclusion, or essentially a linear dynamical system, but with the possibility of some arbitrary, even adversarial disturbance introduced into the system. And what robust control wants to do is it wants to say, let's ensure that we can perform well over all classes of disturbances. This is kind of the typical framework of robust control. So in other words, we have a state, which I'll call here xt. That's, for a car, that would be the position and orientation and the velocities of the car. Maybe at a higher level, it's also the tire velocities, things like this, but it's sort of a typically low dimensional description of the current state of the system. And this equals some linear function of the current, or the time derivative of the state, the way the state evolves is equal to some linear function of the current state plus a linear function of the control, this, the acceleration or the steering, torque on the steering wheel, things like this. Plus, and this point is here, some disturbance, some arbitrary disturbance, WT. And the point here is that the WT actually can be thought of as noise, as sort of random noise, but it also can be thought of as any possible class of disturbance within some allowable set. Okay, and the goal of robust control is to ensure the system will perform well anywhere in this set. Now, one point I want to make here is that this looks like a linear system, but it's actually because this disturbance can depend arbitrarily on the control. It actually does capture nonlinearities within a certain range, and very frequently this is used to sort of capture the error of linearizations of systems, so that you can control the linearized system, but then actually get true bounds for the performance of the true nonlinear system that is underlying your dynamics. And a common model for this disturbance is to assume that not too much about the disturbance. We don't really know what this disturbance could be. It could be somewhat arbitrary, but we are going to assume that we have some known bounds on this disturbance. And a common case here is to say, to assume that we can bound it as some other function. Essentially, we can bound the norm of the disturbance as a function of the state's norm and the control norm, or a linear function of the state norm and the control norm. So this is a very common robust control setting. It's also the basis, actually something very similar is kind of the basis for H-infinity control, if you're familiar with that. But this is sort of a very common setup. And now the goal of robust control is to find a control law that is guaranteed to stabilize the system. In that case, this means drive the system to sort of the zero state, but of course for a more complex system that you sort of model the deltas of your state, maybe from some desired trajectory this way. But the goal is to sort of ensure that you can drive the system to some equilibrium point for any class of disturbance in this set. Okay. And here is how we do it. This is somewhat tongue-in-cheek, so this math is meant to be a little bit funny in some sense, but here's the statement that a lot of robust control makes, or things like this. So given the system specification, so to specify the system, we need to specify the A, B, C, D, G matrices. And by the way, in robust control, we assume that those are known. In other words, we may not know the true actual system, the true actual dynamics, but we assume we know this linear sort of outer bound on the dynamics, and we're going to be stable to that. And so the idea is, given this specification, we want to find a control law, some linear control law. In other words, our controlling input is a linear function of the state, such that the resulting system is stable under any disturbance satisfying this bound. And now's the sort of the punchline, I guess, is that we could find this linear control law by solving a semi-definite program. So we basically solve a semi-definite program in the variables s, y, and mu. S is positive definite, mu is positive, such that essentially this following linear matrix inequality, i.e. semi-definite programming constraint is satisfied. So this whole matrix has to be basically negative definite when you form it. And how we do that doesn't really matter. The point is you can actually plug this into a standard kind of off-the-shelf tool, like something, there's tools like CVXPy and these tools that sort of make this very easy to do. You type up this program, you get out the solution, S and Y there, and then you set your control matrix to be Y times S inverse. So obviously that should just be completely intuitive to everyone, I assume, in this whole talk. So this is somewhat, as I said, somewhat tongue-in-cheek. To be clear, this is the actual semi-definite program we solve here. This is actually how you create a stable controller under this specification, but it isn't really sort of describing what's happening here. So I want to kind of give some intuition about what's happening here, because we're going to use that notion of what's happening here to actually integrate these same kind of guarantees into deep learning systems. So what is happening actually here? Well, what's happening is that we're constructing these methods and all robust control methods to a certain extent. What they're doing is they're constructing what's called a Lyapunov function, right? Which is a positive definite function that is decreasing along trajectories of the system. In other words, this is some sort of positive function. So V is a positive function. It's always positive everywhere. And the time derivative of this function is negative, meaning this function sort of acts as like a potential energy kind of function that has to be decreasing. And it also has to be 0 at the equilibrium point, this function. And so what this means is that if you have these two conditions, then it's just sort of apparent to see that so essentially we're forming a Lyapunov function that is satisfied by the control law. So that means that under this control law, there is some sort of energy function that's always decreasing, and it's 0 at the equilibrium point, which means that no matter what, and no matter how this system is perturbed, it still has to be decreasing. And this is in the instantaneous settings. You can do this here. It has to be decreasing no matter what, And so therefore, if you have this function, if you find this function, then you have guaranteed that your system is stable under any possible disturbance. And that's sort of the nature of how these laws work, or how the techniques work in robust control, kind of at a very high level. And in particular, this big, nasty behemoth of, and this isn't even, I should say, this is nothing compared to what you'll find in your robust control papers, right? You open these things up and they have many, many more blocks, and they look much, much grosser than this. But this sort of, what this semi-definite constraint is doing is it was setting up essentially a semi-definite constraint that guaranteed the conditions of this Lyapunov function. There's a lot of, robust control text that specifies exactly how this works. In fact, actually that variable S that we had before, this sort of positive definite matrix we were solving over, that actually is, or actually the inverse of that is the actual Lyapunov function. So the key point to this is that when you solve one of these robust control specifications, you don't just get out a control law, you also get out a Lyapunov function that certifies that this control law is in fact stable for any possible disturbance in the allowable set. Now, of course, I should emphasize one thing here. It will not always be possible to stabilize these systems, right? There are systems you cannot stabilize. They are, the allowable disturbance is too large, in which case there will be no solution to that previous semi-definite program. But when it is solvable, you can find it by solving the semi-definite program. Okay, and actually, this is actually all I want to say about how these things work, because we'll get back to a little bit maybe in a second, but basically this is the high level here is that what robust control does is it creates a Lyapunov function that is stable under any possible disturbance. And it does so this Lyapunov function applies to a simple linear control policy. Now, important, I mentioned this before, but I just want to re-emphasize this here, is that the system I'm writing here, it looks like a linear system, but it's actually not a linear system. To be very clear, this can model situations where the true dynamics of the system are nonlinear. It's just that you have sort of a linear outer approximation for your system. And again, this is a very common technique in control to develop these sorts of bounds. So we are still, but the important point that we are limiting ourselves to is that we are still using in this setup a linear control law to stabilize the system. So our final control law that we actually created here was still a linear control law. Our action was a linear control of the input state. And so this seems unsatisfying. because a linear control law is not going to be an optimal control law for nonlinear systems. And so it seems like, we might be able to use things like deep reinforcement learning to actually find a nonlinear control law that would be better than the linear controller produced by robust control. That's the potential, at least. So again, the deep RL paradigm typically is that we operate kind of in an unknown system that we can only observe through interaction. And we want to find some policy pi that performs well. This is sort of typical deep RL. And if you operate in a typical deep RL setting, you're kind of out of luck here. Because all you can do in some sense is you have to take potentially unsafe actions because you don't know what your system is. And so that's all you can do is take unsafe actions. So we're going to consider a modified setting here. And what we're going to do is we're going to consider a setting that actually is the same as the robust control settings. We're going to operate in the setting of traditional robust control. But what we're going to try to do is we're going to try to use reinforcement learning methods to learn a better, i.e. a nonlinear policy than the traditional robust control policy, which is this linear policy. But very important here, we want to ensure that our RL method is going to maintain the same robust control guarantees as the robust control law. We cannot sacrifice the safety of the system and the reliability of the system. That would be a non-starter for a lot of domains, right? If you sort of say, oh, well, I can give you a better control law, but all safety is sacrificed. No, we have certain safety conditions that we require of robust control. We want to satisfy those same safety conditions. We just want to do it in the context. We want to do it using methods from deep reinforcement learning to build a more expressive nonlinear control policy. Okay, so how do we go about doing this? The idea actually is very simple. The idea is we want to take the output of the reinforcement learning policy and project it, take whatever output this is, and project it to be stable under the robust control Lyapunov function. So remember, we have a Lyapunov function from our robust control. If we sort of run robust control first, do that first, get a Lyapunov function. Now we have an energy function that we know, or a Lyapunov function that we know can always be decreased. And we know it can be decreased because we know there exists a controller that can do it, a linear one. And so now we want to take our nonlinear control policy and project its output to still be a decrease under this Lyapunov function. And the key idea here is this problem of finding this projection actually is possible. And the reason why is we can look at, essentially, we want this Lyapunov function here, Vt, to be, a V, to be decreasing under the worst case disturbance in the allowable set. And if you, after a little bit of algebra, and it's really actually quite simple algebra, what you can show is that the worst case increase after the worst case disturbance you can have can actually be computed in closed form. It computed in closed form like this as a function of the control input. And importantly, this set here, this set over U, is a set of allowable controls. And by the way, we know there's an element in this set because we know that the linear control law is in the set, or is in the set where it makes this thing negative. We know that this set here is actually ends up being a convex function of U. And what that means is there's a convex set of all controls that specify which allowable controls decrease the Lyapunov function by a certain amount. Okay? And so here's the basic idea. We're going to project the output of the deep network onto the set of these safe controls. Okay, so we're going to take our sort of nominal arbitrary deep network, which could be any function of the state. And we're going to allow it to depend. I just got a notification that participants can now see my screens. Does everyone, can everyone still see it, in fact? Maybe like a thumbs up in the chat if you can still see this.
We can see it perfectly well.
Okay, great. Thank you. Zoom gives odd notifications sometimes. So we're going to take the sort of arbitrary deep network, and we're going to project it to lie in this safe set. In other words, this safe set is a set of all controls that are decreased in the Lyapunov function. We know that our linear control law sits there, but our original neural network policy might lie outside of this, right? Our original policy, if we have an arbitrary neural network, it could output controls that don't satisfy this thing. And what we're going to do then is we're just going to project to lie in the set. Okay. And the key point is, we're not doing this in kind of an after the fact fashion. What we actually want to do is we want to define our policy in the first place to be the concatenation of this projection and the original deep network. And the reason we can do this is that what we can do is we can actually use recent techniques in differentiable optimization to actually build in this projection as a layer in the policy network. We can then differentiate through that projection, just as we would any other layer, and learn a policy end to end that by construction always obeys the same constraints of robust control. Now, if you want to know more about how that projection works, there isn't really time for it in this talk. But last year at NeurIPS, David Duveneau, Matt Johnson, and I presented a tutorial on implicit layers in deep networks, which include things like differentiable optimization. And on this website here, we have a large collection of notes and code examples showing you exactly how to build a differentiable layer like this projection into a deep network. Okay, so let me summarize now the approach before I show some sort of simple results and then close and take questions. So again, here's a summary of the approach. We're given some robust control specification. So we're starting with the same setting as robust control with an unknown dynamical system, but with known bounds on this system. And first, we solve the robust control problem. So as we would act as if we were just solving kind of normal robust control. We then use the output of this robust control synthesis to define a safe set of safe actions that a controller can take at any given state that will still guarantee stability under this robust control specification. Then we define the RL system to be an arbitrary deep network, can be any deep network, followed by a projection onto the safe set. And now we can optimize this RL policy however we want, using whatever technique of reinforcement learning we want. We can use policy search, we can use some model-based techniques, we can use model-based RL, model-free RL, value-based, policy-based, whatever we want. We can use to optimize this policy without any concern that the policy will ever become unsafe. During the whole time, it will always be safe. And importantly, it will have the exact same guarantees as the robust control policy. But because it's a nonlinear policy, it can actually learn behavior that on average, and in the non-worst case, is actually better than the linear control law. So we tested this on 4 simple domains in the paper. And to be clear, this paper really is not about evaluating this in even that large scale system. It's about sort of demonstrating this works. But what we do is we look at a bunch of simple domains here, and we compare the system. We basically compare the performance of the system under normal operation, as well as under adversarial operation. We compare the performance of many different algorithms on this. So let me just show what this looks like. In this case, this will actually be something on just random, we sort of, these nonlinear dynamical inclusions and actually, sorry, norm-bounded linear dynamical inclusions, that's what the N stands for there, where we just choose those A, B, C, D, G matrices randomly, under a certain distribution. The details are in the paper, and then have the real system be a nonlinear system that just satisfies those, that is known to satisfy those bounds. And if we get that, what we sort of have here is we have a bunch, we kind of run a bunch of methods. So LQR, and LQR is a sort of standard control method. MBP and PPO are 2 reinforcement learning methods. And we can think about sort of the traditional non-robust variants of these things, as well as the robust variants of these things. Robust LQR is again, kind of a classical technique, and these robust methods are sort of our approaches here. So this is sort of standard robust control, and our methods are the robust variants of standard reinforcement learning methods. And the first thing to keep in mind here is that if you look, first of all, the cost of the average case cost of MBP and PPO, these are two RL methods, is much lower than the cost of sort of just running RL by itself, right? So that's sort of the first thing to keep in mind, and they're much lower than running sort of robust RL. But the point here is that these ones here are non-robust, and we'll just see a second, they actually can go unstable, the things you sort of don't want to have in these systems. But the important point here is that our methods here, our robust variants of the RL methods, achieve, and this is a log scale, so this is actually a pretty substantial gain here, achieve substantially better average case performance than robust control laws. And this is sort of as expected, because the robust control law here is enforced to use a linear control law. And by using a nonlinear control law, we're able to have more expressive policies that perform better on average in this nonlinear system. But then if we look not just at sort of the average case performance here, but actually worst case performance, what we see is that all the classical methods that are sort of non-robust are unstable. They basically have infinite cost because they diverge. Whereas the robust methods do correctly, I mean, they have worse costs, of course, under worst case inputs. That means they vary farther from the desired set point, but they do so in a way that is still bounded. And importantly, our robust RL methods are able to achieve the same level of robust performance as robust control, while they have better average case performance. And I think this is really sort of a significant step towards bridging these two worlds of deep RL and robust control by incorporating the guarantees of robust control into deep RL. I'll just highlight it briefly here. The results are similar across a number of other test domains here, but really these are sort of very simple domains thus far. And I don't want to, we're testing out in small simulated domains thus far. I think the obvious next step is really seeing how this works in domains where robust control is currently being deployed. So to summarize, I'm very excited about this sort of direction because I think that these two worlds typically have been quite separate, and there's a lot we can actually do though to merge these worlds of the guarantees that you get with robust control, which are why we apply them in kind of relatively small scale, but safety critical systems like actual car systems, like planes, like these sorts of things that we really need controllers to work. We can start to actually think about using reinforcement learning or really any sort of learning-based optimization technique with arbitrary nonlinear policies here, but do so in a way that maintains the same safety considerations we had before. Of course, there's a great deal of work to be done, including in applications, other middle grounds between robust control and RL, and many other areas. But I'm really excited about sort of this as a first step. I think there's a lot more directions to go. So thank you very much. And I think I have time for 1 or 2 questions, but then looks like I took most of my time. So thanks very much, everyone.
Thank you. And I see there is a question in the chat from Jonas. Maybe
yes.
You can. Great.
Yeah,
Please.
so the question is the output of the network after training usually inside or outside of the stable area? So right, so that's a great question. So, maybe during training so first of all, during training, as expected, it's never in the stable area, right? Because it's sort of, when you initialize it randomly, it's never going to give you stable action at first. And if you project it into onto the border stable area and you project it on the border of this thing, yes. Is the main problem then training the RL system to find a good Lyapunov function? So it's right. So again, we're not training the RL system to find the Lyapunov function. We're using the Lyapunov function defined by the robust control specification. We're using that same Lyapunov function as before. We are just always taking the output of the neural network and projecting it onto that safe set. And what we actually, to be a little bit more specific, what we typically do is we actually typically define our network as a delta from the linear control law, so that we have sort of a good initial estimate, and the zero kind of network is sort of a reasonable one. But we train the system like this to sort of always project in. Now, this does create kind of an odd situation where I'm not sure if that's what you're asking, but there is the ability, in some sense, that the network, where it puts the output doesn't matter. All that matters is the projection into this. But what we also do is we also typically do try to add an auxiliary loss that encourages the network to be in here originally, which basically means that the network is we're trying to learn a network that sort of, has stable behavior. We're just also, if it, in the case that it is unstable or in a new domain, maybe in some new state being unstable, we always have this backup of projecting it, and then we train the whole system end to end. So this is sort of why we do it this way. But to be clear, the Lyapunov function itself does not change during learning because that is fixed by the robust control specification.
Awesome, thank you. Maybe a very last question, high-level question with the ask for a short answer. Recently, I think it was DeepMind released a paper which was called Reinforcement Learning is Enough. So yes. Enough for reaching general AI. What is your opinion on that?
Yeah, I mean, this is, Rich and David and this is doing it too. Right? I think these people have been visionaries in the setting of RL, and in some sense, I think I see this paper more as a philosophical point, right, rather than anything else. This is sort of a philosophy paper that sort of says that what are the conditions needed for intelligence? Like what are the things we need for intelligence? And arguing essentially that the paradigm of reinforcement learning is in some sense logically or philosophically sufficient for this. I think it's not saying that, and that would be true. I mean, maybe our brains have the same kind of RL method at some point, and so it's enough in some normal sense, but it's not enough for practical use in real systems. I mean, just the fact that humans aren't very intelligent, right? I don't myself control, the low layer control laws of my car or of an airplane, right? We actually use controllers for very good reason for that. They're much faster. They're very stable. They have these nice properties. So yes, maybe RL is enough in some sense for general intelligence, but it's really a philosophical point. The bigger point being that what we want practically are stabilizing safe systems. They've been very, very effective in doing some amazing things. I don't think we could use just human intelligence to fly to the moon, right? It's a good thing we had some control laws to do that. And I think so enough is sort of a hard question, right? But I think that we're going to want these things no matter what. I'll answer the other questions that are in the chat now, just in the chat, because I know we're going to move on to the next talk.
Perfect. Thank you again, Siko. And please stop